Hello, everyone. My name is Shariff, and I want to talk about our recent research about low-order approximation of flexible structures. First of all, here is the outline of my talk, and first I will introduce the motivation behind my research, and then I will discuss about the mathematical modeling, and there I discuss about the main goal of the proposed method for calculating the low-order approximation of the systems. And there I studied two problems, standard Cauchy problem and boundary control system. In the third section, I will apply my proposed method to two numerical cases. The first one wave equation, and the second one two-dimensional Kirchhoff plate. And in the fourth section, I will point out some concluding remarks, and in the final part, I will point out my dissemination activities. The motivation behind my research is feed-forward control designs for flexible motion systems like wafer stage, which is used in semiconductor industry. Actually, it was in previous stage of my research in ConFlex, and there we found difficulty in calculating an accurate model description at low frequency, and there we propose a method for calculating accurate model description. In frequency domain, the mechanical motion systems can be introduced in terms of equation number 1, where G2 is representative of the mass or inertia function. G1 comes from the velocity term, and the rest is include the structural dynamics of the systems. And for the aim of feed-forward control design, we need to include the flexibilities of the systems at low frequencies. The core idea of this talk is to calculate G0 as a compliance function. It is the low order representative of flexibilities of the systems, and once this function is defined, the system can be fully determined at low frequency. And here in time domain, I propose a general abstract formulation for this function. In terms of frequency domain, we can use by calculating this limit, while for higher dimensions and with more complex PDEs, the calculation of this limit can be quite hard. So we switch to time domain approach. And the first part for this method is that by checking the time domain response of these systems, we can get this function in equation number 3, and we can claim that this is the expected solution that we expect from our mechanical systems. And the procedure in time domain starts with its omega of assumed, and then I will apply these for class of equations that I consider. In the first part, I will work with this equation number 4, which has a damping term, and then I will investigate the calculating the compliance function for these systems. First, we consider that our state space is a Hilbert space, and our A0 operator is a non-negative self-adjoint operator, which has a compact resolvent and also with initial boundary conditions, and the boundary operator is inside the domain. And like other systems, second order systems, first I reformulated to the standard systems on an extended state space, and then by checking the semi-group property of this equation, it can be guaranteed that for every initial conditions, we can get a unique solution for Z and correspondingly for omega and our solution. And for developing the approach, first, since the operator is a compact resolvent, we can consider that our space span in the orthonormal basis functions of the operator, and then by using the constant input on the domain of our systems and considering the predicted solution that we take into account, we get this set of equations for each of the solution components. And the aim is to calculate omega 2, omega 1, and omega 0. And the omega 0 is representing the flexibilities of the systems. To start with, first, we assume that the phi 1 to phi n lies in the kernel of the operator A0, and it arises from the 0 eigenvalues. And then we can see that for the first equation, it gives us that omega 2 is in the kernel of A0, and so it spans the phi 1 to phi n. Similarly, for the second equation, we get the similar results that omega 1 is in the kernel of A0. However, if you take a look to the last equation, which comes from the stable part of the solution, the stable part of the solution comes from the stable resonances of the systems, which can take infinite number of resonances and modes that goes to 0 at by time. So our main goal is to calculate the first components of the solution. But considering this, we can see that the initial condition of the stable part is equal to the omega 1. And so by considering this condition and the second equation, we can get that omega 1 is equal to 0. For the third equation, we can see that omega 0 as a compliance function is the initial condition for the stable part. And by considering this, we can claim that omega 0 is also a stable and static response of the structural dynamics. And then we can, by using this condition and using the orthogonality of the stable and unstable part, we can calculate the solution structure uniquely. Where you can see here that as we checked, omega 2 is the function of orthonormal basis from phi 1 to phi n, and omega 1 is equal to 0, and omega 0 stays in the stable part. From this part, we can get an impression that omega 1 can be neglected, while in the second part, we can see that this function plays a role in frequency domain approach. As a second part, for the evaluation of my method, I used the frequency domain approach for checking the components that I gained from time domain. First of all, for checking I checked in the Laplace domain and calculating the transfer function, and then by considering the output, not the transfer function, we can get this equation, and then by applying that the solution is in the Hilbert space, we can get that the omega of S is a function of orthonormal basis, and by using Fourier expansions of the solution, I can get the solution in this format. And then by separating the eigenvalues of stable and unstable part, the components of the omega of S can be determined in this form. And of course, by checking the variables that here are identified, I can get that G2 and G1 and G0, which are representing from omega 2 and omega 0 in time domain, yielded to the identical results as we get in the time domain. And this in examples, we can see that the amount of calculations can get reduced significantly in time domain, while in frequency domain we had difficulty to deal with irrational transfer functions. As a second case, I studied boundary control problem, where the control input is located on the boundaries of the domain, and also here again we consider a damping term. As a first step, I first define a new operator, including the domain of A and domain of A and the intersection with the kernel of a boundary operator. And then by defining the B, a bounded linear operator with these properties, we can claim that this equation is a boundary control problem, and we can, by defining a new variable, we can solve the solution for the V variable, and then consecutively for the omega parameter. And of course, here we consider this equation for the relation between the A and A0 operator, where Q is a linear operator from the domain of A to U as the input space. And then we can claim that if V is a classical solution for this equation, we can say that omega is as well a classical solution for this equation, and we can continue with the method that we use in time domain approach for the Cauchy problem. And here I should mention that this epsilon is included in the initial condition, since B with the assumption that we use for the B operator, we need to claim that the initial condition also lies in the domain of A0. And so we assume that epsilon minus BU0 is in the domain of A0. And once once this is solved, we can find out the omega, and specifically omega 0, as a compliance function of our systems. So by assuming a classical solution, we do the similar procedure for the boundary control problem. And here, with non-homogeneous boundary conditions, I can get the solution components and solution structure in this format. And we can see that here the solution are as expected, and omega 2 is lies in the unstable part, while omega 0, as our main goal, stays in the stable part of the solution, while the coefficients of the solution components comes from the Q operator, where it comes from the boundaries of the domain. Here in this section, I evaluate the results for the boundary control problem with a frequency domain approach. And similarly, I check the transfer function from U to omega from the previous equation, and then by checking the Fourier expansions and orthonormal basis of the solution, I checked the omega of S to find out the components separately. And here I guess that the solution for G2 and G0 are similar to the part that we gain in time domain in our proposed method, while for the G1 comes non-zero, and this may result in this. We found it in our examples that I explain it later, and here this G1 as a non-zero part will affect the frequency domain approach, because there the initial conditions is makes the initial conditions for the velocity term may not exist, and in the next part I studied two examples. For the first one, as a starting point, I use one-dimensional wave equation, and here I said that our operator is the second order with respect to the x, and second order derivative with respect to x, and the input is applied on the boundaries. For the time domain approach, which is a quicker way to calculate the structure of the response, as we propose in the theorem, we get that omega 1 is equal to 0, and for the omega 1 as a mass or inertia function, we can find out the solution simply by solving it for one-dimensional case, and for the third one, we can get the omega 0 not uniquely, and with the extra condition that we propose in the theorem, we can find out the solution uniquely, and that was the contribution of the time domain proposed method. Here, in simple words, we can say that for the one-dimensional case, we can say that since omega 0 is in the stable part, it does not grow through the intended interval, and by applying this condition, we can get the unique compliance function. But for higher dimensions and more complicated PTs, this can include calculating the eigenvalues and eigenfunctions of the systems. And here it is shown the calculation of compliance function with the time domain method, and also numerical finite element method, which shows that after stabilizing the systems, we can get the results are identical and consistent with each other. And here, again, for the frequency domain, where we get the non-zero velocity term, I calculated the transfer function for wave equation, and by checking these limits, as I said in the first slide for the definition of compliance function, here I get the compliance function identical to the previous method, while for the G1 we get a non-zero function. And as a second example, which was our main goal, I studied Kirchhoff plate model, and here the operator is the self-adjoint bi-Laplacian operator, and D is a physical property, and we studied it numerically and considering all of the coefficients, and our control input is located on one of the edges of our plate. And in the time domain, since the frequency approach becomes quite complicated, we studied the time domain approach, and by considering the set of equations. Can I continue?
Just go on.
Okay, by considering the set of equations and the third equation, which includes the compliance function, needs to be checked with the boundary as a boundary control problem, and there I define a new operator and also B, and then for solving this equation, I switch to the numerical part for solving it for the Kirchhoff plate equation, and for the B, we just guaranteed that this the solution for this B for this specific example exists, and we can claim that it is a boundary control problem. And for this part, I studied with finite element method, and for the inertia function, we get this numerical plot. And also for the compliance function, we get this type of deformation for our plate. And by checking these functions, we can fully determine our solution in low frequency, and it can be used for the purpose of feed-forward control designs. And to wrap up, I worked with, in this presentation, I checked a general abstract formulation for the mechanical flexible systems at a low frequency, and I studied the low order approximation of for boundary control problems, and at the last I studied a numerical solution for the compliance function of the Kirchhoff plate. And about my dissemination activities, my last publication was presented in IFAC World Conference, and now I am completing and preparing my reports for submitting to a journal. And also I presented in the European Control Conference in 2020. And of course, about my secondments, I unfortunately could not complete my last secondments in Warwick. And about my next journey, I would like to continue research in academia, and of course, I am eager to have a position as a research and development in industrial part as well. And thank you for listening to my presentation.